Well, welcome to the first of our higher level content videos on option D7. So if you're doing standard level, turn this video off and go do something else. Higher level, stick around and we will be talking about chirality, and then in a later video we'll be applying that to a specific case study known as Taxol that we need to know about. So essentially for this topic we are looking at another drug, which is Taxol, which is a drug used to treat different forms of cancer. It's a natural product derived drug, so it occurs in yew trees, and we will look at how it is synthetically produced now or semi-synthetically produced as part of our case study. We'll look at the use of chiral auxiliaries for its synthesis because it has many chiral centers, and the way that they're used in order to be able to synthesize optically active substances. We will also look at how Taxol is obtained, its description of its synthesis, and the explanation of how we use a polarimeter to identify enantiomers. Just a reminder also that the structure of this is the very large molecule on the last page of section 37, so about page 39 of your data booklet. So let's get started. Before we can talk about Taxol in detail, we need to kind of remember what isomers are and introduce a couple of new types. So largely there are three types of isomers. Structural isomers, which we have already met in our study of organic chemistry, where we can have branches and put things together in a different way. So same molecular formula, but a different structural arrangement in terms of the length of chain or branches, things like that. Geometric isomers are cis and trans, and we will see these again in higher level organics, so we're not going to look at them in detail here now, but they are a type of isomer that we will come into contact with later. And then also optical isomers, which are enantiomers, and that's what we're going to look at as the focus of this video. So enantiomers are essentially exactly the same molecular formula, with things connected in the same way, except that they are a mirror image of each other. So if we look at this one here, if you imagined a mirror here, we have essentially reflected this across the mirror plane. So the hydrogen is here, CO2H here, but the NH2 is now behind, and the CH3 is here. Essentially, they're like our left and right hand. They appear to be the same, but they are non-superimposable. So optical isomers are what we call chiral objects, okay? So they are optical and named that way because of the way they interact with light. So if you've ever worn polarized sunglasses or anything like that, essentially what happens is the light passes through a polarizer, which causes it to now move in a single plane. So where we have this light source here, the light bulb, it produces light that scatters in all directions. When we put a polarizer in front of it, we select for one particular direction. So this up and down. Now substances that are optically active, okay, or optical isomers, or substances that are chiral, which it makes them optically active. When we pass this plane polarized light through a sample of them, they will either rotate to the left or rotate to the right. And we can use a computer to detect this level of rotation. Okay, so we can detect the presence of chiral enantiomers by the way in which they interact with plane polarized light due to the angle of rotation that that light goes through. So two molecules are considered chiral when they have exactly the same molecular formula, but they have a different three-dimensional arrangement in space. Okay, so they're non-superimposable mirror images. All optical isomers must contain a chiral carbon. We cannot have an optical isomer if it doesn't contain a chiral carbon. And this is simply a carbon atom which is bonded to 4 different groups around that central atom. Okay, so we can't have any of the same groups bonded to a carbon or it's not chiral. Okay, and then the pair of these compounds are referred to as enantiomers, which is the name we give our optical isomers. So if we look at these in terms of highlighting the chiral centers in the following molecules, remembering that every vertice is a carbon, okay, and this would be a carbon, and that those carbons must have hydrogens to meet the number of bonds that are there. We can fill these in. Clearly, anything that is a CH3 cannot be chiral because it has 3 of the same group. So this one's not going to be chiral. This one's not going to be chiral. This one's not going to be chiral. This one here is bonded to a CH3 and then another CH3, so that one's not chiral. This carbon in here will be bonded to a hydrogen, a CH3, a bromine, and then this CH3, which means that it's bonded to 4 different groups, so it will in fact be chiral. Okay, so I want you to pause the video, go through and see if you can identify each of the chiral carbons in these molecules. Once you've identified them by putting an asterisk, which is the way that we usually identify chiral carbons, we'll put a little asterisk next to it, come back and see what the answers are. Okay, hopefully you had a go and here are our answers. So as we identified in A, this is our chiral carbon here. In B, we can see this one goes to a CH2, CH3. So this would be one group. This is a CH3, this is a different group. This one is now a CH2 and an OH, which makes it different to the left-hand side. So that is a different group, and of course we would have our hydrogen, which means 4 different groups. Okay, now if we look at C, we can see here we go off to an OH, CH2, CH3. This arm is different to the one on the left-hand side. The OH is a different group, and then the hydrogen. So this one would be chiral, and then this one is also chiral because it has 1, 2, 3, 4 different groups. So check your assignments for each of these. Hopefully you found the 3 in the ring structure. The catch with rings is to remember I start here and this half of the ring is different to this half of the ring, so they're considered 2 different groups, and then this one here, okay, and then this one we go around to a different number of bonds between this carbon here and the carbonyl, and then we come around to this one here, but also we have the stereochemistry, this in and out of the hydrogen. So we have a hydrogen above the ring here and a hydrogen below the ring here, which actually makes them different. Anytime we have symmetry through a molecule, we won't have chirality there or on the carbons that are around it. Okay, so whenever you're looking for a chiral carbon, you need to look at the whole molecule and the group bonded to the carbon, not just the one immediately next door. You need to follow it through the molecule and see if there's any difference, because it's the whole group as we go out that we're looking at, that we're looking for that difference in. Okay, so once we have our carbon attached to 4 different groups, this is known as a chiral center. Okay, that carbon is known as a chiral center. We must have at least 1 chiral center in a molecule for it to be an enantiomer. Molecules with more than 1 chiral center may not always be chiral. They can cancel each other out. But mostly you'll be asked to identify ones where you'll just be identifying 1 or 2 chiral centers within a molecule. So chiral centers are often marked with an asterisk, as I said before, and we use this stereochemistry framework to show them. So hopefully, we've talked about this before, but we haven't really learnt it, in that if I have a carbon and I have a straight line here in here, these ones are in the plane. That is to say that they are in the same plane as the screen or the piece of paper that you're drawing on. And then if I have a dashed line, these ones are going in behind or basically poking back into the paper. they would be pointing backwards into the paper, and then a solid wedge is going to be sticking out. Okay, so this is basically saying that it would be poking out of the plane of the paper to give us an idea of what 3 dimensions are. Okay, so we should try and remember to draw our chiral centers with this because it helps us draw the mirror image. So if we look at which of the following enantiomers of the following substance, okay, so you need to now try and think, what would my flip of this be? How would I find it out? Okay, and in this case, you would look at the mirror image. However, for this one, straight away we can see that there's no chiral center because there are 2 hydrogens. We don't have a chiral center, which means it won't have a non-superimposable enantiomer. Okay, so it doesn't, because it's got the 2 hydrogens on it, it means that we don't have 4 different groups to carbon, so we don't have a chiral center, so we're not going to have a non-superimposable enantiomer on it. Trick question. Okay, what about this one? Which of the following molecules is achiral? And achiral means not chiral, which means not having a chiral center. So if we have a look here, we can see this carbon here would be not chiral. This one's going to be non-chiral. This one as well, we've got a double bond, so it can't be chiral either. So there's no chiral centers in this one. If we have a look here, 1, 2, 3, this would be chiral, so 2 can't be our answer. This is a chiral carbon. This is a chiral carbon, and this one here, and we have a chiral carbon there. So the only answer must be A, which is number 1 is achiral. It does not contain a chiral center. Okay, let's just quickly go through the properties because this is getting a little long. But essentially, if you can imagine, enantiomers are the same molecular formula and they're essentially bonded in the same way, except they have a different arrangement in 3-dimensional space. This means that they have identical physical and chemical properties. Because they contain the same functional groups, they contain the same types of molecules, the reactions they undergo will be the same. They'll have the same molar mass, they'll have the same density, those kinds of things. So they're not going to differ in any of those ways. They'll have the same melting point, boiling point. The only way that enantiomers differ is by their optical activity, so that is to say their interaction with light, and we talked about plane polarized light. So they will rotate plane polarized light. One enantiomer will rotate it to the left, the other will rotate it to the right. Okay, so the way they interact with light is different, and the way they interact with other chiral substances is different. So enantiomers interact with other compounds differently, so they produce products that have different chemical or physical properties. So this is particularly important in biological systems because they'll interact with receptors and enzymes in a different way. Okay, so because enzymes are 3-dimensionally specific, then chiral molecules will interact with those environments in a very different way. Some enantiomers of drugs are completely inactive, while other enantiomers will work well as painkillers. And we've also heard about thalidomide, where one enantiomer reduces morning sickness, but the other actually cause bad neural defects in developing babies. Okay, so enantiomeric substances are very important when we look at drug development. Okay, so we can tell them apart by using a polarimeter, okay, which is something that measures the rotation of light. Okay, so we pass light that is going maybe straight up and down through the sample, and then we measure the angle to which it is rotated. If we have a mixture, a racemic mixture, which means it contains both isomers, the rotation of the light will be cancelled out. So we won't see any rotation. But if we have a pure enantiomer, okay, so an R enantiomer will rotate to the right, and S enantiomer will rotate to the left. Okay, and this is what we mean by them being optically active. Okay, so we've built some models, we've had a look. There are a couple of other videos that you could watch here, and we will practice drawing these structures in class as well. But hopefully you've got a better idea of what it means for a substance to be chiral, and an ability to be able to identify these centers in molecules.